So in this chapter, we are learning about something called Lewis theory. Lewis theory is one of the several theories that we have in chemistry that help us describe bonding, chemical bonding. And this is actually the simplest theory, and it's very powerful even though it's so simple. It's based off of valence electrons, and it emphasizes the use of valence electrons to explain bonding. So in this theory, we draw something called Lewis structures. These are our models that help us kind of convey how chemicals bond together, atoms bond together. And you can also call them electron dot structures. They have dots, you'll see why. And they also help us predict many properties of molecules like stability, shape, and size, and polarity, which are things that we will learn about in this chapter. Before we get to Lewis theory, we're going to go over the different types of bonds. So we've kind of gone over these earlier in the semester, but we're going to delve a little bit deeper into them. So just to help you recall, ionic bonds occur when you have one electron completely transferred to another atom from one atom. The properties of ionic compounds are that they are crystalline solids. They have very, very high melting points, so above 300 degrees Celsius. They can conduct electricity once they're dissolved in water. So remember how we learned how ionic compounds dissociate in water and then they turn into their ionic forms in water? They actually conduct electricity very well because they are in those ionic forms, while the solid state doesn't conduct electricity. So just think of how table saw, it's really harmless. Like when it's as a solid, nothing really happens to it. It doesn't burn, right? It takes a very high temperature to melt it. And again, they're very soluble in water. So how do ionic compounds form? Well, we know that they're made up of nonmetals plus a metal, so an anion plus that cation. The anion is the nonmetal because they have a very high electron affinity, so they like gaining that electron, right? Remember, it helps them have the configuration of a noble gas. And then the cation will lose the electron easily because they have very low first ionization energy. Oh, that should have an E right next to it, sorry. So next we have covalent bonds. This is whenever we have sharing of electrons. So here for an example, we have just H2O. Specifically, it's ice, so it's the solid version. Within this, we have nonmetals, so oxygen and hydrogen, and they're bound together through covalent bonds. So whenever covalent bonds occur, whenever you have atoms that have very similar ionization energies and electron affinity, so neither of them necessarily I like to say neither of them like to hog the electron, right? Neither of them likes to take that electron completely. They kind of both equally can share it between them. So another example is just an H2 molecule. So remember all those have no fear of ice cold beer molecules, those are all bound by covalent bonds. So for example, H2. And remember that elements, the way that they usually bind together is so that they end up looking like a noble gas electronically. So some properties of covalent bonds. They are actually horrible conductors. They do not conduct any electricity in the solid or liquid state. Their melting points are the opposite of ionic compounds, so they're kind of usually low. You can find them in many states at room temperature, solid, liquid, gas. And we know that since both atoms don't necessarily have a low ionization energy or a high electron affinity, then they'll just share it equally. Here are some examples, very common examples of different compounds that have covalent bonds within them, so molecular compounds. So how do these covalent compounds actually form? So you will have typically nonmetals, and what ends up happening is, for example, whenever you have two different hydrogen atoms, and they each have their own little 1s orbital and their electron within that 1s orbital. what has to happen in order for that bond to form is they have to overlap. So they have to get close enough so that they end up overlapping and those electrons are kind of shared between the both. Here's an example of two p orbitals, specifically two p orbitals, but there's two of them, right? You have two separate f atoms, and you need these p orbitals to overlap in order to have that bond form. Now, if these atoms get too close, then that also kind of like backfires, so they won't bond if they get too close to each other. So they have to be kind of in a very sweet spot where they're not too close to each other, but that they're close enough so that both of the atoms are happy and they're sharing that electron. And then finally, we have metallic bonds. We haven't talked about these at all, I believe, but there's nothing really much to it. So for metals, what you have is something called an electron sea. I know that's very small, but you have kind of just electrons kind of floating out there like a sea. So the simplest theory to describe this metallic bonding involves the metal atoms releasing their valence electrons. So again, the electrons are kind of just floating out there and they're kind of shared like a pool. So again, like water, like a sea. And that's pretty much what happens for metallic bonding. Oh, so specifically this happens for whenever you have a solid metal like in its standard state. So for example, whenever you have solid sodium by itself, then this is how the atoms are bound together through metallic bonds. This is just showing you a kind of closer zoomed up version of that. So again, the organization of these electrons is like a sea, and we call the electrons, we term them as being delocalized, meaning that they're not in one specific place. They're just not in one specific local place. That's what delocalized means. So now we can actually start talking about Lewis symbols. So we know about the different bonds, and Lewis structures can actually describe all of those different bonds. So Lewis symbols are essentially the chemical symbol with the valence electrons around them. So here, for example, we have oxygen. We know that oxygen's chemical symbol is just an O. And then we know that oxygen has 6 valence electrons. So we place these 6 electrons as dots around that oxygen. So these dots represent valence electrons. So there's kind of a specific manner that you place these electrons. Now, as you keep drawing Lewis structures, you're going to end up just drawing a lot of these electrons as bonds, so you don't necessarily have to worry about it too much later on. But the customary way of doing this is you pair the first 2 dots as the s orbital electrons, and then from there you place, so for example, this nitrogen, these first 2 dots are the s orbital electrons. From there you just place 1, 1, and 1 as the first 3 p electrons, and then anything else after that is filling in whatever's left of the p orbital. So for example, this fluorine has these first 2 s orbital electrons, and then you have these p filled in. So this is just a refresher. How do we determine valence electrons? So this is something that students kind of get lost on a lot of times, but it's very simple. All you have to do is look at the periodic table. Ignore the transition metals. Again, they're like very unpredictable. You don't have to look at those. But for main group elements, and remember main group elements are the first 2, which is alkali and alkaline earth, and then everything else beyond that in the p block are also main group elements. So first group, 1 valence electron. Second group, 2 valence electrons. Third group, this is boron's group, 3, 4, 5, 6, 7, 8. So noble gases have 8. Halogens have 7, oxygen's group has 6, nitrogen's group has 5, carbon's group has 4. So this comes from the electron configuration. So remember, everything has, not everything, but many elements, almost everything, has a noble gas core, and then whatever's left are valence electrons. So that is where these are coming from. So we've learned throughout the semester many times that elements like to have configurations or look electronically like noble gases. And we end up kind of establishing this rule called the octet rule from that. So it's the tendency of main group atoms to form enough bonds to obtain 8 valence electrons. Why 8? And that has to do again with the noble gas configuration, and it has to do with the fact that noble gases, their valence electrons will include a S2 and then P6. So the N stands for any energy level, so it can be like 1s, sorry, not 1s, but 2s2 to P6. That makes up a total of 8 electrons, so that's 6 plus that 2. And then basically any atom that makes bonds in order to have those 8 electrons like noble gases, we establish that as our octet rule. So we can predict the number of bonds that an atom can form in order to reach that octet. So we have some very common bonding patterns, and here I have some very again, common elements that form a typical amount of bonds. So for carbon likes to form 4 bonds. Carbon has 4 valence electrons, so in order to reach those 8 valence electrons, like the octet rule, it's going to form 4 bonds. Total, it's going to have 8 electrons around it. So here I want to point out, you can count out those 8 electrons around. Even though it's sharing them with those chlorines, total it has 8. Same thing with silicon, and silicon, it has the same pattern because it's in carbon's group. What about nitrogen, oxygen, fluorine? Nitrogen will form 3 bonds, oxygen will form 2 bonds, and halogens, fluorine is a halogen, will form 1 bond. So even though we have those very typical common bonding patterns, they will almost always have those 8 electrons around it. They're the happiest. That's how I like to describe it. They're the happiest whenever they have those 8 electrons. We do have exceptions to the octet rule. So we have molecules that end up having an odd number of electrons around it. These are called odd electron molecules. We have central atoms, and we're going to describe what a central atom is, but we have central atoms that will have less than 8 electrons around it, and then we have central atoms that will have more than 8 electrons around it. We call this hypervalent. Hyper just means a lot, like many. Valent means like the electrons around it. Electron deficient describes itself. So the basics of Lewis symbols. We know that Lewis symbols are comprised of the chemical symbol, and then we have the number of valence electrons around it depicted as dots. So, for example, a sodium atom. This is a neutral sodium atom. What happens whenever it becomes an ion? We can actually depict this in Lewis symbols. So specifically for this Lewis symbol for this, when it's a neutral sodium atom, it will just have 1 valence electron. It's in the first group, so 1 valence electron. Whenever it turns into a cation, it loses that electron, so you end up having just a plus charge. Compared to halogens, they have 7 valence electrons. They like to gain 1 electron, and then they'll end up having those 8 around it, and now they're happy. Here's calcium. It likes to lose 2 electrons. Here's sulfur. It likes to gain 2 electrons. So for ionic compounds, we have to kind of get into a little bit about how they actually bond together. So here we have some Lewis symbols of ions coming together to form an ionic compound. So we have potassium, it has 1 valence electron. We have chlorine, it has 7 valence electrons. Potassium gives up that 1 valence electron, gives it to chlorine. Now we have chlorine happy, potassium happy, and they form potassium chloride. Now how does this actually form? It forms through something called a crystal lattice. So the crystal lattice is held together by the electrostatic attractions. Electrostatic just has to do with charges. So the fact that this turns positive and this turns negative, those are the electrostatic attractions. So the way that this actually forms maximizes those interaction so that they can have the maximum possible interactions between the positive and the negative. So because of that, we don't actually have a ionic molecule. We never say ionic molecules. We always say ionic compounds. And that has to do with the fact that this is a network of ions. It's not just one little unit of like one potassium and one chlorine. It's a giant network of them interacting with each other. So you can see here how they come together. This is actually sodium and chloride, but same idea. They come together and then they form this, again, giant network of a bunch of ions. So that's why we say there's no particular ionic molecule. All we can possibly have is an empirical formula, so it's a ratio of the ions. Here we are showing the different steps. So whenever ionic compounds form, you actually have a series of steps. So you have to have things be gaseous, then they have to ionize, and then they have to come together. So again, this has to do with like Hess's law, and we actually call this the Born-Haber cycle for producing NaCl from solid sodium and chlorine gas.